So our second speaker this afternoon is Georgii Chernykh, and his title is On the Rigidity of Some Hirzebruch Genera.
Yes. Okay. I would like to thank all organizers of this wonderful program and the nice workshop for the opportunity to give me a talk here. Thank you very much. Is my microphone on? Some people in Zoom. I think yes. I think yes. People online, is my microphone is on?
Is the microphone on?
On? I think yes. I think yes. In fact, Chuchen said me that it's on. I don't know. Okay, let's start, and let me briefly recall what the cobordism ring is. The cobordism ring, the complex cobordism ring, is the ring of stably complex manifold. What's stably complex manifold? It's manifold stably complex structure, and stably complex structure on manifold. It's complex structure on direct sum of tangent bundle and some trivial real bundle up to addition of trivial complex summands. Okay, and if we have such two manifolds, we can consider cobordism relation between them, and two stably complex manifolds are cobordant if the disjoint union of M and N with opposite stably complex structure is the boundary of some stably complex manifold with boundary. And it's a equivalence relation, and we can then define a quotient set. And in fact, this set has two operations: addition and multiplication. Addition induced by disjoint union and multiplication induced by Cartesian product. And we obtain some evenly graded, in fact, commutative ring, cobordism ring. It's isomorphic to a polynomial ring with one generator in each even dimension, the result of Novick and Milner. And so it's the ring of complex cobordism. Okay. We have not what?
We go back.
Yes.
On the definition. So first of all, I believe that usually one does identify different complex structures that are isomorphic as complex vector bundles.
Yes.
And
yes.
If you do that, then the almost complex structure does not induce an orientation. And since you wrote n bar, I suspect maybe you're reversing orientation rather than.
No, it's induced orientation.
I'm sorry. No, it does not if you allow complex bundle
No, complex
isomorphisms.
Complex automorphism preserve orientation. No?
Fiber-wise on the bundle, but not on the manifold, because the vector bundle isomorphism might not come.
No,
Yeah. So for example, take the three-dimensional sphere with its tangent bundle is trivial. Just add a copy of R, to make it, and then you can identify it in different ways with the trivial bundle C2. Some of them.
Yes, we have.
And they could, if you have it representative of J, it does give you an orientation, but equivalent J's could induce opposite orientations. I sort of suspect you have fixed an orientation as well.
No, different stably complex structure can be induced different orientations, of course.
No, equivalent stable complex structures.
Equivalence, it's up to.
Yeah, they could induce. I'm just saying. I suspect that you have chosen orientation. I suspect the n bar is opposite orientation just from looking at the symbols.
And bar with the so-called opposite stably complex structure,
I
it
don't.
induced opposite.
So maybe we
yes.
can talk about that later.
I will not, but
I'm just not sure.
There are no details here because I have no time. Sorry.
Yeah. Okay.
But,
sorry.
We have notion of opposite stably complex structure. I believe that stably complex structure, the equivalence class of it, induced orientation. In fact.
Yeah, this Rn is also oriented.
Representative does.
Okay. I will discuss it with you later. Okay, and what's Hirzebruch genera? It's if we have some graded commutative algebra over rationals, then and cobordism ring, then complex Hirzebruch genus for us is just a ring homomorphism from cobordism ring to ring. It's some function on manifolds, on stably complex manifolds, which is invariant with respect to cobordism, which and taken disjoint union to sums and Cartesian products to product in R. So, and this is theorem that complex genera are in bijection with the power series with coefficients in R with the first term X. It's kind of a result of Hirzebruch, and in one direction, if we have genus phi, then we can apply it coefficient wise to this genus, to this power series. It's Mischenker's formula, and obtain some power series with coefficients in R, and it's the inverse series for corresponding power series F. And in the other direction, we have, if we have power series F, we can consider the classical formula. It's symmetric expression in variables xi, and we can express it in elementary symmetric functions. And if we replace elementary symmetric functions by Chern classes, we obtain some characteristic class with coefficients in R. And if we apply it to tangent bundle and pair with a fundamental class, we obtain some element in R. And one can check that this is a multiplicative and additive function in cobordism ring. So it's the bijection. Okay, so we have genera and corresponding power series. Okay, what's equivalent extension of this genera? We can similarly consider complex cobordism ring of TK invariant equivariant manifolds. We consider stably complex manifolds with the action of torus. We fix torus, we fix K, we fix some torus, and consider manifolds with some action of torus. And in fact, so I need some light. If we have an action of torus on M, we have induced action on tangent bundle, and if we consider the trivial action on the trivial summand, we obtain some action of torus on this sum, and then we consider complex structures on this sum, which is equivalent with respect to this action. And this is our definition of equivariant stably complex manifolds, and we can then consider the usual notion of cobordism of such manifolds. So we obtain the equivariant cobordism ring then. Okay, and in fact we have some comparison homomorphism from this ring to so-called homotopical equivariant cobordism, complex cobordism ring. I will not define what is it because I have no time, in fact. But as in non-equivariant case, we have, of course, that cobordism is not just a ring; it's a cohomology theory, and we can define it in geometric way and in homotopical way as homotopic groups of some spaces, some spectra, and then we have Pontryagin Tom. It's PT, Pontryagin Tom comparison collapsing map from geometric one to homotopical one, and in non-equivariant case, it's isomorphism is Tom theorem, and but in equivariant case, it's not isomorphism because of lack of transitarity, but we also have this comparison homomorphism from our cobordism ring to some homotopical ring, and then we have homomorphism from this homotopical ring to the ordinary cobordism of classification space of torus, which is just a power series in K variables with coefficients ordinary complex cobordism ring. So we obtain this homomorphism. We call this the universal complex toric genus. In fact, it's injective. It's a result of Komisani and Hanke about inductivity of the first one and the Loeffler of the inductivity of the second one. So we have some injective homomorphism from our equivariant complex cobordism ring of manifolds with torus action to power series with coefficients in ordinary complex cobordism ring. Okay, and then if we have some ordinary genera from complex cobordism ring to R, then we can consider the following composition, the universal homomorphism, and then two things. On coefficients, we consider phi, omega u to R, and then we consider also some change of coordinates because F is invertible power series. It's just a change of coordinates. It's convenient in some formulas. So, and so we from ordinary genus obtain some equivalent extension. It's homomorphism, ring homomorphism from equivalent cobordism ring to some extension of the original ring, its power series. Okay, it's the definition of equivalent extension of the ordinary genus, and then so it takes some manifold with Torus action and sends it to some power series. But it may happen that on some manifold, the value of this extension is just a constant power series. And then we say that the original genus is rigid on some TK manifold if the value of its equivalent extension is constant power series on it. In fact, in this situation, this constant is just the value of the original genus on this manifold. And this is because, in fact, I didn't say that we have such formula for universal toric genus. Here, okay, maybe, okay, it's not important. But we have this formula. This formula, Buchstaber, Panov, and Rey, they obtained the formula. They described explicitly the coefficients of the universal toric genus. It's some power series with coefficient in complex cobordism, and we have some coefficients, and they explicitly described these coefficients as some stably complex manifold. In fact, these stably complex manifolds. So it's okay. I will say about this later, but now it's important that the first term is just m, and if we apply phi, change of coordinates do not matter here, then we obtain that the first term of the equivalent extension is phi of m. Okay. Yes, and why this property rigidity is important? Because in fact we have that this property is equivalent to the fiber-wise multiplicativity of the genus for any fiber bundle with fiber m. By definition, genus is multiplicative for trivial bundles, but in some cases it's multiplicative for any fiber bundle, and in fact it's when it's rigid. In fact, this theorem holds by some technical assumption. If genus is multiplicative for any bundle, then it's of course rigid. It follows from this formula because this these coefficients are in fact total space of bundles with fiber m with some base, and this base is cobordant to 0 in cobordism ring. And so if phi is multiplicative for any bundle, then we can apply phi to this formula with some change of coordinates, but it does not matter. And obtain that equivalent extension of phi of m is phi of m with some phi of this, and but phi of this is 0, because if phi is multiplicative, we have phi of these coefficients is phi of m times phi of this, and this is 0, phi of 0 is 0, and so we obtain that all higher terms vanish, and we obtain that phi is of course rigid. This its value of its extension is constant, and but in opposite direction, it's we need some assumptions, because, for example, Kodaira constructed. Okay, we have example of genus. Its signature of multiplication homology is well known. It's well known genus, and of course, it's Hirzebruch theorem that the genus is multiplicative for any bundle with a trivial monodromy, with trivial action of fundamental group of base on the homology of fiber, and then this theorem can be applied for these bundles because these bases are simply connected, and then we obtain that signature is rigid for any m. But Kodaira constructed some complex surfaces, the four-dimensional real manifolds, such that which are bundles over some Riemann surfaces with fiber Riemann surfaces, and then because of the dimensional reasons, signature is 0 on base and 0 on fibers. But Kodaira proved that the signature is not 0 for any of these surface, complex surface. So a signature is rigid on any m, but not multiplicative on any bundles. And this counterexample of Kodaira is counterexample for this theorem without some technical assumption, and for Borel-Hirzebruch theorem without assumption on monodromy. So we need to be careful here. So, and but this okay, this technical assumption is just this complex cobordism of the classification group of the classification space of structure group is torsion free. Torsion free. If it's torsion free, then rigid genus is multiplicative for any rigid genus is multiplicative for any bundles with this property. Okay. And the main part of my talk, it's the following Bouchabert-Panofried result. It's localization formula, which expresses the equivalent extension of some genus on some manifold with isolated fixed points in terms of fixed point data. If we have manifold with torus sections with some finite fixed points, then in any fixed point we have tangent representation of the torus, and so we have some weights. It's some integer vectors. It's weights here. It's k-dimensional weights, and here it's formal inner product. It's just linear combinations of variables x1, xk with coefficients are coordinates of the weights, and then we consider f of this. F is power series. We consider f of this integral combination and consider this fraction, then product. Yes. And then we can also define some sign in any fixed point, and then we consider the sum with signs of such products. And this is theorem that this expression is in fact equivalent extension of original genus on the manifold M. And you can see that these fractions are in fact not power series, but it's a corollary of this result that the sum with signs of such products, it's in fact a power series. It's not a fraction. It has no fraction parts, in fact. Okay, and then if we obtain some question, for example, we can ask if we have some manifold or some class of manifolds, we can ask which genera are rigid on these manifolds. And the theorem, from the theorem, we can obtain that this question can be reduced to the algebraic analytic question of the solution of some rigidity equation. We can consider power s, power series f, and consider this rigidity equation. This must be constant in the case of rigidity, and we obtain some equation on f on power series, and we can try to solve it and answer the question about rigidity of some genera on some manifolds. Okay, there are some examples. For example, for example, we have such genus. It's genus with this power series for some values of parameters. This is, for example, signature, for which parameters it's an exercise, and the theorem of Musin that this kind of genera are universal rigid genera. It means that such genera are rigid on any manifolds, and if such genus is rigid on any manifolds, then it has this form. In fact, it was proved by Bouchabert and Bunikov that it's enough rigidity on any only on CP2, in fact, and non-zero value on CP2. It's kind of interesting result, but it's typical result in some sense, because it's might happen that if you consider some general rigid question about rigidity on some class of manifolds, you can maybe find some finite set of manifolds, and if genus is rigid on them, then it's rigid on infinite class, and this is result of such type. And we yes, and this is the following example. It's genus will be we will need this genus. So oriented elliptic genus, it's some genus yes of such form. Then it corresponds to power series or elliptic sign. What's the elliptic sign? We of course have some analytic definition, but for us it's just an odd power series satisfies this biquadratic equation for derivative and itself. for some values it's again it's signature, but yes, in the result of Chernykh and Stolz, for example, that this genus is a universal genus rigid on quaternionic projective plane. Quaternionic projective plane is not stably complex, it's just oriented, but some genera can be defined not only on stably complex manifolds, but on any oriented manifolds, and this genera corresponds exactly to odd power series. Elliptic sign is odd, so we can define this elliptic genus oriented on any oriented manifold, and then one can prove that this is the genus is a universal rigid genus on quaternionic projective plane. So okay, but we need the complex elliptic genus, and complex elliptic genus is genus with 4 parameters. It means that corresponding power series have coefficients in 4 parameters, or equivalently that genus taken value in 4 parameter polynomial ring. And what is it? It's complex elliptic. It's universal complex elliptic genus, and it was defined by Krejcir and Hon independently. And here we using point of view of Krejcir. So Krejcir just defined the corresponding power series in such form. And what is it? Exponential. It's exponential, but what is it? This function in denominator. What it's very well known in analytic theory of special functions, Baker-Hager function. But for us, it's just we have the following formal definition. For example, we can define formally what is the Weierstrass P function. It's just function of such form which satisfying the following. Okay, again, some equation. And if we define Weierstrass P function, then we can define Weierstrass sigma function, Weierstrass zeta function, and then we can define what is this function. And one can check that if we define this function in such way that then this fraction has coefficients in 3 parameters, where parameters is p, p derivative, and g2, where g3, but g3 is a polynomial in the first 3 parameters, so we do not need them. Okay, we don't need it. Okay, so it's some formal definition. And why we need this genus? Because Krejcir defined this and proved this the following theorem. Krejcir proved that this genus is reached on any SU manifold. SU manifold, stably complex manifold with the 0 first Chern class. And then Krejcir proved that if we consider such genus with such a corresponding power series, then it's rigid on any SU manifold. And in fact, if we have, okay, it's not important. And the theorem of Buchstaber-Poincaré that the Krejcir genus vanishes on any quasi-toric SU manifold. You can check that if you have a toric manifold, then a toric variety, projective toric variety, then it cannot be SU. It cannot have 0 third Chern class. But there are a lot of quasi-toric SU manifolds, in fact. But Krejcir genus vanishes on all of them. Okay. Okay, we have, okay. Now we need to consider the cobordism ring of SU manifolds. We have SU manifolds because we have cobordism relation between them, and we can define cobordism SU ring, SU cobordism ring. And it's in fact it's much more complicated ring than the complex cobordism one, and it has torsion, and even modular torsion is not polynomial, but all torsion is 2 torsion, and if we invert 2, then this ring is polynomial. It has such generators. We can choose these generators to be integer, to be represented by actual SU manifold. And this is some low dimensional picture. We have generator Y2. Y2 can be represented by K3 surface. By K3 surface. It's some quartic in CP3. But there are no toric actions on such surfaces, so we cannot apply our toric techniques for this generator. More interesting is the following generator Y3. It can be represented by S6. S6 has the canonical, it's well-known almost complex structure, following from this representation of its homogeneous space of some Lie groups. And in fact, it's almost complex. And of course, S6 has no second homology, so the first Chernykh class is 0, and it's a SU manifold. And in fact, one can check that it represents the generator of your body's ring. And we have the action of the maximal torus of SU3 on S6. And then we can apply our approach of localization formula for the question about rigidity on this manifold S6. And it's the result of Buchstaber, Panov, and Ray again, that if genus phi is reached on S6, then if it's non-zero on this manifold, then it's a Krzyver genus with parameter B2 non-zero. So if Krzyver genus is reached on any SU manifold, but if genus is reached on any on only one SU manifold at 6 and non-zero on it, then it's a Krzyver genus too. But if it's 0 on S6, then it's just, we can only say that its corresponding power series is a multiplication of exponential and some odd power series. And I need to say here that what is the exceptional case here? If B2 is 0, then Krzyver power series is just exponential times elliptic sign. And so, but what about the higher generators? Y4 can be represented by by complex Grassmannian G24 with some twisted stably complex structure. And I will not talk about this. But all higher generators can be in fact represented by quasi-toric SU manifolds. This is the result of Liu and Panov. And this result is following from the it's the place where toric topology arises in our story. And Liu and Panov constructed some two families of quasi-toric SU manifolds. It's okay, let's understand. We have, for example, it's quasi-toric manifolds over products of simplices. For example, what is L tilde? We have CP2K1, just projective space, and we can consider sum of line bundles over it, and then we consider productivization of this sum of line bundles. This is some toric manifold, but it's not SU manifold. But we know that its tangent bundle stably is the sum of some line bundles, and then we can replace some of these line bundles by its complex conjugate. It corresponds to replacement of the corresponding characteristic matrix, and in fact we obtain some quasi-toric manifold. Okay, yes, it's right. Some quasi-toric manifold which is SU manifold, and over product of simplices. And in the case of N tilde, we have the similar construction. So it's some twisted of toric manifolds. It's not toric, it's quasi-toric. And the second important result, that if we have two quasi-toric manifolds, we can consider its connected sum. It's also quasi-toric manifold, and it represents the sum of Borges classes. So if we have some co-Borges classes which is represented by quasi-toric manifolds, then we can represent by quasi-toric manifolds all integral linear combinations. And from these results, Liu and Panov proved that we can represent any generators in SU manifold in SU co-Borges ring. Okay, but we need only the first one. Y5. Y5 is just the class of L tilde 2, 3. It's a quasi-toric manifold, and for quasi-toric manifolds we know all fixed point data. It has I don't know. It has, I think, 12. It has 12. Yes, it has 12 fixed points with some weights in each of them. But and we can write directly the rigidity equation, and from some analysis of these equations, we can, in some sense, solve it and obtain the following result: that if our genus phi is rigid on S6 and 0 on S6, so the corresponding power series is the multiplication of exponential on some odd power series. And if phi is rigid on this manifold, quasi-toric manifold, then in fact this odd power series is just the elliptic sign. So we obtain the following result that Hirzebruch genus is the universal genus which is rigid on S6 and this SU quasitoric manifolds. And in particular, it's universal SU rigid genus. If some genus is rigid on any SU manifold, then it's Hirzebruch genus. And in the following slide, I wanted to say something about the oriented case, but I think I have no time. Yes.
Maybe 1 more minute.
No. Okay. It's not then. Okay. Okay. It's not sponsor. Okay.